Now we are going to see how the BJT can be used as an amplifier. The basis for the amplifier application is the fact that when the BJT is operated in the active mode, it acts as a voltage-controlled current source. Therefore, changes in the base emitter voltage VBE give rise to changes in the collector current IC. However, as we have studied in Module 3, the amplification has to be linear. Otherwise, the signal, that is the output signal, is going to be distorted. However, the transistor's behavior is highly nonlinear. So what we do is that we bias the circuit to operate at a DC base emitter voltage VBE and a corresponding DC collector current IC. This bias point is deliberately kept in the middle of the characteristic curve. Why? Because that part of the curve is almost linear and also allows for a healthy voltage swing at the output. So if you superimpose a small signal, small v, small be, on the DC voltage VBE, it is going to be amplified linearly, and even though the output is the current, we can simply pass the current through a resistor to achieve voltage amplification. So now that we've got our definitions out of the way, let us see graphically how we are going to be achieving that. We are not going to go into too much detail on this topic here, particularly since this has been covered quite extensively in the third module, which is for the MOSFET. A link is provided to you in the instructor's notes if you want to go through that. Take a look at this configuration, Common-Emitter. What we are going to do is that we are going to change our voltage VBE, and correspondingly our current is going to change, and by passing this current through resistor RC, we are going to obtain the voltage VCE. So this becomes a case of voltage amplification. Now here is the graph, and I have marked some regions for you and some points, and we are going to be discussing them one by one. Now V0 can be expressed by this equation, VCC minus ICRC. Now let's start at point X. This is when Vi is 0. This continues until Vi reaches a value 0.5. This is the point Y. For Vi greater than 0.5, the transistor starts to conduct. IC increases and consequently V0 decreases. We can write an equation for IC. This one, IC equals Is e to the power VBE over VT. Now active mode operation ends when the collector voltage, that is V0, falls by 0.4 volts or so below that of the base, that is Vi. At this point, the CBJ, that is the common base junction, turns on, the point Z on your screen, and so the transistor enters the saturation region. Now did you wonder why we call it the saturation region? Notice that further increasing Vi has a negligible effect on V0. So this is why we call the output voltage at Z VCE sat. It has reached saturation and does not decrease anymore. The collector current also at that point remains nearly constant. We can find an expression for IC sat, VCC minus VCE sat divided by RC. Pretty simple. Next up we find the voltage gain. For that we need to express V0 in terms of Vi. Here we are at the bottom of your screen. We are going to differentiate that dV0 over dVi at the point Q. Remember that the voltage gain is specific to that point. To explain the voltage gain graphically, we see the blue line on our graph. The slope of this tangent to the transfer curve at point Q is basically the voltage gain of the amplifier for small input signals around Q. So finding the derivative, we get this expression minus bracket open VCC minus VCE bracket close divided by VT. Notice that all of these values are DC values. Why? Because we are evaluating our voltage gain at a particular point Q. Now let's move on to operation as a switch.